So just before we start the last lecture, I wanted to thank a few OSU staff members have helped organize this. Most of you have been in correspondence with at least one of them, but Carrie Moore, Don Jones, and Shanda Wagner all did a lot to get us all here. I want to publicly acknowledge them. Also want to thank Ariel for doing all the videos. I know it's kind of a high pressure job because if you forget to hit record, we lose it forever. But, so thank you to Ariel. And thank you, Tyler, for looking at it. And then without further ado, we'll come to Alice's last lecture on higher summer groups.
Yeah. I also want to thank everyone who's made this possible. All the faculty at OSU have been involved in the planning of this. This has been a really wonderful week and a really cool opportunity, I think, for both me and Julia. Anyhow, so today I want to talk a little bit about higher summer groups. So my last two lectures I was talking exclusively about two summer groups. And the sort of crux of my project is not in the two summer layer, but somewhere higher up. How do we go from control of the two summer group to the 4 summer group, 8 summer group, etc. And we do it through the Castle-State pairing, as Ariel just introduced. And so to start today, I want to give a relatively explicit example where we can understand at least the first Castle-State pairing pretty well to understand the 4 summer groups. So this will be a 4 summer example. And the setup is going to look very familiar. We are again going to work in a grid. To start, let's take E to be an elliptic curve. And we're going to assume that E2 is isomorphic to Z mod 2Z squared as a Galois module. This just makes the parameterization at the 2 summer layer much easier. So it's good to always assume it. V will be the same thing as it was yesterday. It'll be the primes 2 and infinity together with the primes of band reduction.
Yeah, if you want E to Q to be that one too.
Yeah, absolutely. Okay. And like yesterday, I'm going to take x1 through xk to be disjoint sets of primes. X will be their product. And we're also going to assume that the xi do not meet V. Okay. Great. And now, yesterday we made this assumption. So for A, dividing A, where capital A is the product of the primes in V, we're still going to assume that A over Pi, this Legendre symbol, stays constant over the axis of primes xi. So this needs to hold for all Pi and Pi prime and xi, and I less than or equal to k. But the second assumption is going to be different. Yesterday we wanted to prove an equidistribution statement about 2 summer groups, and so we assumed that the Legendre symbols Pi over Pj changed a lot, changed maximally. Today I want to talk about 4 summer groups, and so I want the 2 summer groups to stay put. And because of that, I'm going to assume that for all I not equal to j, we have that Pi over Pj is equal to Pi prime over Pj prime. And I want this to hold for any 2 primes in xi and for all tuples of 2 primes in xj. Okay. So So this is a weird condition. What you should imagine in your head is that it's actually pretty hard to make a grid that looks like this. In particular, if we're considering numbers up through h, this restriction actually means that except for one of these sets xi, all the others have to have size bounded by about log h, or even smaller. And so we end up with these sort of long but skinny grids. Those are sort of the situation where we do this work. But that's still good enough to actually say something about the higher Selmer groups. This restriction isn't such a big deal in the end. Okay. And so our goal is to understand the 4 Selmer groups. In this family, the 2 Selmer group remains constant. We've fixed the 2 pieces of information that determine the 2 Selmer group. And so our final assumption is that for all d inside of x, so again, we think of d as both a tuple, but also as a product. We assume that cell 2 of ED, which lies inside of H1GQ ED2. ED2 looks like 2 copies of Z mod 2Z, so this is isomorphic to Q cross over Q cross squared times Q cross over Q cross squared. So we have this map, and so, but we assume that for all G under the map, we're going to assume that cell 2 ED is generated by P1, 1, and 1 P2. So that these 2 tuples generate our 2 Selmer group modulo the image of rational torsion. The image of rational torsion in this case adds 2 extra dimensions that do not matter, and they are terrible. I really do not care for them. So we're just going to get rid of those. Like this 2 Selmer group, it's sort of a trivial piece of the Selmer group. But once we remove those, we assume that this quotient is generated inside of this product of groups, first by the tuple P11, and then also by the tuple 1P2. So a two-dimensional Selmer group. And so the statistical question is, how does the Castle-State pairing of the 2 Selmer group parameterized by P11 and the 2 Selmer group, 2 Selmer element parameterized by 1P2, how does this vary? Let me write down CT for Castle-State. Vary as D equals P1 varies in X. And so the guess is that this pairing should be is 1/2 for 50% of D, and 0 for 50% of D. And what this would imply is that we have R4 of ED is equal to 0 for, all these probabilities are approximate, for about 50% of T, and is equal to 2 for about 50%. And so this will give us something sort of in line with the Markov predictions of day one for this specific family. And you can imagine that by doing this sort of calculation, not just in this family, but in more general ones with larger two-Selmer groups, that's when we would be able to actually get the full control we want to understand the four Selmer groups. But this is a good starting place. And so the question is, how can we control this Castle-Tate pairing in this family of D inside of X? And the key calculation is to, we're going to compare this pairing for D equals P1, P2, P3, and D equals P1, P2, P3 prime. So in this case, we're focusing on a grid with just 3 axes. For simplicity, you could have the other axes, but they don't play a role in this particular calculation. So let's assume K equals 3 for now. And so we have already used 2 primes in our description of this two-Selmer group. We have our two Selmer elements. And now we're asking what changing a 3rd prime does. The reason why this sort of makes sense to do is because it means that our inputs into the Castle-Tate pairing aren't shifting at all. The only thing that's changing is sort of the pairing itself. And that simplifies things. Okay, and so one calculation that's going to come up is, if you remember from Ariel's talk, part of defining the Castle-Tate pairing was choosing a lift of your 2 Selmer element, or I guess in his talk, an M Selmer element, choosing the lift of it to the M times N Shaffer-Tate group or Selmer group. And so what we're going to do first is we're going to compare what these lifts look like between these 2 twists. I'm going to call this D prime. And so setup is we're going to take X as an Ariel's talk, but this is going to be the element inside of H1 GQ ED2 associated to P11. And just as easily, we could say that X is associated. This group is just canonically isomorphic to H1 GQ ED prime 2. Okay, and then in Ariel's talk, the first step is to choose some X0 inside of H1 GQ ED4 such that 2x0 is equal to x. And yes, go ahead and choose that. What I'm going to do now is I'm going to give you a recipe to find this lift for the other twist. And the starting point is I'm going to make an assumption. So we're going to assume that there is some gamma. So this is just going to be a function going from GQ to the 2 torsion of E, such that when we look at D gamma, which is going to be defined as, okay, so D gamma, let me just recall the definition of this. D gamma is the cocycle on 2 variables, sigma and tau, given from essentially checking whether the cross homomorphism condition is satisfied. And so in particular, this co-boundary applied to a cocycle is 0. Okay, and so we're going to assume that there is some gamma such that D gamma is equal to the cup product between chi P3, P3 prime, which is something inside of the cocycles, the 1 cocycles valued in plus minus 1, cupped with X, which, if you recall, this is inside of, well, let's just say H1 GQ of E D2. And recall that X, this element is associated to just to P1, and in particular, if you find such a gamma for the point P1, P2, P3, you can reuse it for any other choice of P2 since it doesn't actually depend on P2. But let's just assume that such a gamma exists.
Just to understand what this is.
Yeah.
So in our case, ED2 is just Z2 plus Z2 plus Z2, so everything is just Holmes.
Yeah, everything is just Holmes.
And then is this just cut product, just the product?
It's just a product, yeah. So, not so bad in this case. And in fact, back when I was first doing this, being able to really grapple with these cochains was very important. And so like having these explicit homomorphism descriptions was very, very useful.
Is that like an explicit way of thinking about? Okay, never mind.
Sorry, what was that?
No, that's my question.
Okay. All right. And so let's suppose that we found this gamma. Then the crazy calculation that turns out to work out is, okay, so on Monday I defined maps beta D. So beta D always goes from ED to E, and similarly beta D prime. And in general, even if you have something like x0, so dx0 is equal to 0, but for example, if we do this twist, so that beta dx0, instead of having values in ED4, it has values in E4, this coboundary is not usually 0. Another way of saying this is we can't just reuse this lift exactly for the other twists of E. We need to find a new twist, or a new element. But here's a recipe. We have this wonderful element gamma. Then the claim is that if we take x naught prime equal to first we have beta d prime -1 and beta d applied to x naught. So this this takes your 4 cocycle valued in ED and turns it into a cochain valued in ED prime 4. If we take x naught prime equal to this plus the same beta d prime inverse, but now applied to this element gamma, under these circumstances, we have that dx naught prime is equal to 0, i.e. We have that x naught prime is a lift to h1 gted prime 4 it's a lift of our element. So going from this gamma, from this choice of gamma, we're able to produce a lift of x naught prime from starting from our lift x naught. Okay. And so the reason we wanted these lifts was to be able to define a Castle state pairing. And now we can't. So first we have this pairing is equal to the sum over all places of our rational places of the local tape pairing between the restriction to P of our x naught. So this is going to be first the pairing for D, restriction to P of x naught minus something that locally a local lift of x. So that's what goes on the left, and then on the right is a y, where y is going to be associated to 1p2. So this is the formula that holds for the pairing at D. And then we can ask for the same pairing at D prime. And we get almost the exact same expression. So the only thing that changes is that instead of x naught, we have to use x naught prime. Oh, I should put a restriction here as well. Okay, so we have two very similar looking formulae, and now we can take their difference. And what that gives us is it gives us that the difference between these Castle state pairings is equal to the sum. And so these sums are both over all places, but when you do these calculations out, almost all of the places actually go away. So these two terms match up if you set things up correctly for all primes except for P2. P2 is the one prime where things don't work out. And the reason P2 is showing up is because this element is ramified only at P2. So this element is now playing a role. It's sort of influencing where these terms can be non-trivial. So since we're assuming that, the difference between these Castle state pairings turns out to be given by the invariant map applied at P2 of our element gamma, which is a one cochain. So one cochains in general are going to be a little bit unpleasant to work with, but once we take the restriction of it, it looks a little nicer. So the restriction to P2 of our one cochain gamma, and then this is going to be cupped with the restriction to P2 of y. So we end up with this formula. And the thing that holds about this is this expression is determined by what gamma is at the Frobenius element associated to P2. So gamma is a function from the absolute Galois group of Q to E2, and so what this is saying is if x2 is large enough so that Chebytarov holds, this expression is 1/2 for 50% of P2, and 0 for 50% of P2. So the difference in the Castle state pairing between P1, P2, P3, and P1, P2, P3 prime is equal to 0 for half of the P2 and equal to 1/2 for half of the P2.
Is it obvious one is only two possibilities for gamma?
Sorry, what was
Is it
that?
obvious one is only two possibilities for gamma, so I thought we could.
Are these the only two possibilities for what gamma can?
Yeah, is it like that?
Oh, inside of E2. So not from exactly how I've defined it, but so gamma is defined to lie inside of E2, but how it's set up is it's really, you're just looking for a cochain whose co-boundary is equal to the cup product, not really of a quadratic character with E2, but really just two quadratic characters. And so in that sense, it can really only take two values. In the more general setup where I actually wrote it down, yeah, it could take 4 values, but in any case, 2 of those values will give 0 and 2 of them will give 1/2. Does that help?
Yeah, that helps.
Okay. And so if we consider statistically what this tells us, what we find is that in the family of P1 times, so we have P2 varying a lot so that Chebytarov can hold. And then we only have 2 choices of P3. We have P3 and P3 prime. But in this family, the 4 Selmer rank is equal to 0 for a proportion between 25% and 75%. And the idea here is, here's a little picture. So I've got P2 changing in this direction. And so what this theorem is saying is that along this tower, for half of the choices of P2, the Castle state pairing at these 2 points will be the same. And at half of the choices, the pairing will be different. And so at the 50% where it's different, we always get, so yeah, let's say we have a difference here, same. So something like this. So at the points where the pairings are different, one of them is forced to be 1/2 and the other is forced to be 0. It doesn't matter statistically which one is which. In each case, you get 1 of each. But in the similar case, where they're the same, you don't know what's happening. And in fact, like, if God was cruel, he can make all of the similar ones be 0 all the time. And in that case, you would end up with the 75% proportion. Similarly, you could be cruel in the other way and then make in all the cases where they're the same, have it be 1/2, and then you'd get the 25%. So all you know from this picture is that the proportion is between 25% and 75%. Okay, so that's sort of indicating that this relative information isn't perfect. But the strategy to get past this isn't so bad. If we instead look at the family of P1 times x2 as before, but now instead of just having 2 primes over here, we start varying over a larger selection of primes. So I guess I put 4 primes here, so or 4 apostrophes, so this is 5 primes. And if we look at this family and do the same game as best we can, we're going to get better proportions than we did previously. Maybe in this case, we play the same game and the proportions we get are between 30% and 70%. And so not too much better, but a little bit better. And the point is that if we just keep making this axis bigger and using more and more control, we're actually eventually going to get pretty close to 50%, to within whatever error we want of 50%. So combinatorially, that's the idea that sort of powers the 4-Selmer machine. So this was the calculation I wanted to do for 4 Selmer groups. Before I continue, are there any questions? Okay. So I briefly wanted to talk in this final lecture about the history of these sorts of methods. And so the history can sort of be broken into 2 chunks. There is some work that's been done for 2 Selmer groups, and then also a little bit of work that's been done for 4 Selmer. And so the 2 Selmer results really go back to Gerth. And what Gerth did is in grids of D, satisfying assumption 2 from the last 2 lectures, Gareth was able to find the distribution of the 4 class ranks, say of the imaginary quadratic fields. And so he did this for sort of general K and let K go to infinity, and he did this in the mid-80s. And the only reason that he's not given credit for figuring out the distribution of these groups is he then didn't go and prove that the grids he was working on sort of covered the natural numbers evenly. And in fact, they didn't, because they satisfied assumption 2. So he was looking specifically at families of the form x1 times x2 up through xk, where x1 through xk were all the primes up to a given point each. That was what he was doing. So that was this was sort of the first instance of grids really playing a role in any sort of calculation. This was in the mid-80s. Heath Brown. computed the two Selmer groups of the quadratic twists of the congruent number curve. And this is from 1994. And this is a very powerful method that he used, a very analytical method. And one thing that I find interesting about it is it's sort of a vein of research here which doesn't use grids really at all. So this methods of Heath Brown were extended to study the two part of the class groups, or the four torsion of the class groups. This was done by Friedrich-Kluners. So yeah, Heath Brown introduced the method for studying Selmer groups that was then taken up by Friedrich-Kluners. And so the difference between Friedrich-Kluners' work and Gerth's work is that Friedrich-Kluners applied to natural families rather than grids. So yeah, in this, on the not grid side of things, people started with Selmer groups and then went to class groups. Meanwhile, on the griddy side of things, people started with class groups in this work of Gerth, and then went to Selmer groups. So the next step was Swinnerton-Dyer in the mid-2000s, I think maybe 2006. And he, again, under sort of nebulous restrictions resembling assumption 2, he studies cell 2 of ED under the assumption that the rational 2 torsion is as large as possible. And this assumption he used for the same reason that everybody likes it, which is it makes studying us writing down elements in the two Selmer group particularly straightforward. And again, this was for grids. And Swinnerton-Dyer's work then gave way to two major papers later on. The first one is Klagsbrun, Maser, and Rubin, who removed the torsion assumption, or more specifically, Klagsbrun, Maser, and Rubin, this was in 2013, they aren't able to study all elliptic curves, but they are able to study what is classically the most difficult elliptic curves, namely elliptic curves with no 2 torsion at all, no rational 2 torsion. And they did this for grids. And then the other main thing that this paper with Swinnerton-Dyer led to was a paper of Keynes from around the same time, which is the distribution of two Selmer groups in the family considered by for elliptic curves satisfying this condition star. But for natural families of D. Okay, and so this particular paper is one that's particularly close to my heart. And the reason for that is this was sort of the first indication that if you understood something just for grids, you could do enough analytic number theory to actually be able to prove it in natural families. So yes, using the Swinnerton-Dyer paper as input, Kane is really able to finish the job. And so I would say my two Selmer work is definitely most indebted to Kane, and by extension Swinnerton-Dyer, and by extension Gareth. So that's sort of the complete picture on the two Selmer side. Maybe I'll also mention work of Jack Kliss, who studied something analogous to the Fugger-Klunert problem, but in the setting of cyclic degree L extensions. He was able to find statistics of the first layer of the L infinity class group there. But yeah, that's sort of all the work that was done for the two Selmer groups. And now I want to say at least something about the four Selmer groups. And here, the theorem I want to focus on has to do with governing fields. And so this is a theorem which I'm going to credit to Rede and Stavenhagen. And what they said is that given any non-zero integer d, one can find a Galois extension L over Q such that for any prime P that's not 2 and doesn't divide D, such that for any prime we can determine the structure of the A class group of the quadratic field root dp from the conjugacy class of frob p inside of the Galois group L over Q. So for four torsion, this statement, very, very important, very, very super important. You cannot determine the whole class group from a field in this way. That would be very strange. This only works up through 8 torsion. For 4 torsion, this should be sort of intuitive. Starting with the 2 torsion, this is very intuitive. This is Gauss genus theory. We know exactly what's on the left-hand side all the time. For 4 torsion, we have certain requirements in terms of Legendre symbols to calculate the structure of the 4 class group. And then what Rede and then later Stavenhagen, so Stavenhagen's results from the mid-90s, figured out is that you could actually construct your field L to go one step further. You can go up to the 8 torsion level. People, Cohn and Ligarius once conjectured that you could actually go even further up and figure out the 16 torsion, 32 torsion, etc. People no longer believe that this is the case. There's strong evidence otherwise by Koymans and Milovic. And how you should think about this result is, the analog for this statement is we similarly have such an L for determining the structure of the 4 Selmer group of an elliptic curve twisted by D and P. So E is fixed and D is fixed, but then we have a field L over Q such that the splitting of P inside of that field determines the structure of this 4 Selmer group. And this is by the Cassels-Tate argument I just gave you. And so before my work, the one person who I've made progress on this is this mathematician Hemingway, who he worked this out in his PhD thesis in I think the mid-2000s, in some special cases. Okay, so this is just to give you some context for where my results are sitting. And then if you want to go up to 8 Selmer, you'll run into a problem. There really isn't a lot about 8 Selmer groups in the literature. And I think the reason for this is that the actual algebraic results that you can prove for 8 Selmer groups are much, much weaker. Like, this is a pretty strong result. You have good control on 4 Selmer groups. But for higher Selmer groups, the control you can get is not so good. And the only reason that I'm able to go from those results to an understanding of the distribution of 2 to the k Selmer groups is through a healthy amount of combinatorics. So, I want to finish today with what this picture looks like at the next level up. Okay, and so the picture to look at the 8 Selmer level, let's assume we're in the same family that we started the lecture with, where we have an elliptic curve with full rational 2 torsion, and we have our grid x equals x1 times x2, etc. So we're still looking there, and we're specifically interested in the case where the 2 Selmer group is generated by this P11, which we called x, and 1P2, which we called y. And so in this case, we're still going to assume that k is equal to 3. And we're going to look at a cube of twists. So we're going to be taking d from P1 prime, P2 prime, and P3 prime. And we're going to, it'll be nice to have names for each of these things. So let's go ahead and take D empty set to be P1, P2, P3. D1 to be P1 prime, P2, P3. D12 to be P1 prime, P2 prime, P3, etc. So we're denoting the subset of primes where we're looking at Pi prime by using the subscript. Okay. And so here is the proposition. So suppose we can choose a lift, and it's going to be excess inside of the Selmer group, the 4 Selmer group of E, twisted by ds. Suppose we can choose a lift excess of x, and suppose we can do this for all S, a subset of 1, 2, 3, except the case so at 7 of the sets that we've written down, we're assuming that we can choose a lift of our 2 Selmer element x. So we have these 7 elements XS. Suppose further, because things would be too easy if we didn't have some more crazy assumptions, we're going to assume that, well, the first miracle that happens is that when we sum up over faces, so we've assembled a cube of twists, and when you sum up these cocycles over faces, after untwisting using the beta d, you always get a cocycle back, just by sort of, I'll say magic. And so that's useful. And the extra assumption we need to have is that when we sum over the three faces of the cube that we have that don't have 1, 2, 3 in them, these cocycles actually add up to 0. So beta empty set, x empty set, I guess this is a D empty set. I'm going to remove the D from this notation. So just beta 1 x1 plus beta 2 x2 plus beta 1 2 x1 2. Let's suppose that this is 0. Similarly, beta beta empty set x empty set plus beta 1 x1 plus beta 3 x3 plus beta 1 3 x1 3. This is also equal to 0. And finally, assume that beta empty set x empty set plus beta 2 x2 plus beta 3 x3 plus beta 2 3 x2 3. So these are sort of independent assumptions that we need to add to the situation. Then we get two claims. First, if we take x1, 2, 3 to be the sum over all s not equal to 1, 2, 3 of beta 1, 2, 3 of this, again, more crazy cochain manipulations, but this lies inside of the 4 Selmer group of the one twist that we have skipped. And it is in fact a lift of x. And then the second condition is that we can write the sum of the Castle's tape pairings over this family, so over this whole cube of our elements, four torsions, so xs and y for the d associated to s. This again is going to be something controllable using the Chevatarov density theorem. Okay. So this is the big theorem for the 8 Selmer level. And you should notice that this theorem is really delicate. Like just to draw out what's happening. What's happening is we have a cube of twists, and for 7 of the twists in this family, we have a nice 4 cocycle. We have a nice lift, and on the 3 faces that I've drawn, we know that the sum of those cocycles is 0. And then the conclusion of the theorem is that we can figure out a 4 cocycle for the one remaining point in the cube, and then we can find what the sum of the Castle's tape pairings over the whole cube is. And what you might notice about this situation is it doesn't look like you learned that much. Like you start with 7 pieces of information, 1 for each vertex. And even on top of that, you have this extra condition that things are adding to 0. So And from all of that together, you get one piece of information. So a lot goes in and a little bit comes out. But here, the same moral that was true in the four torsion of the four Selmer group calculation is true. This is just what you can find out if you consider one cube. The next step is to, instead of having just P1, P1 prime and P2, P2 prime, P3, P3 prime, let's make each of those axes bigger. And as you make those axes bigger and bigger and bigger, suddenly this sort of sparse picture becomes a lot more filled in. And you end up getting more and more information about the distribution of 8 Selmer groups across this grid from your Chebytarov information. And so, because of this, as you make the grid larger and larger, Chebytarov tells you more and more, and the worst case statistics on the 8 Selmer groups get closer and closer to the statistics you expect. That among the cases where the 4 Selmer group has rank 2, the 8 Selmer group has a rank 0 half the time and rank 2 half the time. So yeah, that's the full 8 Selmer picture. If you wanted the 16 Selmer picture, you would need a hypercube. If you want the 32 one, you need the thing after a hypercube. And so it goes. But yeah, so I just wanted to give you some indication of where we go with the sort of 2 Selmer techniques. And if nothing else, I wanted this week to sort of be an advertisement for grids, which I think are sort of the natural way to think about these sorts of problems. You start in a grid, and suddenly things work at least a little bit more cleanly. So thank you. Yes.
Does the sum of the remaining cases also sum to 0 when you fill it?
Yes, absolutely. So if I were going to do this for real, you should put signs in here to be extra super careful. But I don't think you need them in this case because everything is like 2 torsion. You put yes, the sums over the remaining face. If you set things up correctly, they'll be 0.
How restrictive is that condition?
It's not so restrictive. It's a big pain, but you can, if you're sort of steadfast, you can work through it. Specifically, as I mentioned, when you add up your 4 lifts across a face, you do always get a cocycle. And when you consider that cocycle, it obeys the local conditions for the Selmer groups of these points at most places. The only places that are skipped are sort of the ones that are actually being changed. So the sum of these 4 vertices lands in a slightly relaxed 2 Selmer group. And so because of this, how I sort of think about it when you're working on the full grid X is that you're painting your vertices a certain set of colors. And the number of colors you need depend both on how many, sort of the dimension of hypercube you need, which depends on how far down the Selmer group you're going, and also on the 2 Selmer ring, because that influences how many things these things can sum up to. But yeah, it's the number of colors is just in that, in terms of those. And then if you have, 7 vertices all the same color, the one remaining vertex is also that color, and everything sums nicely.
What about how you get from k equals 3 to k equals log h?
So k equals, so you're asking,
Like how do you bootstrap this up to now deal with larger grid with more prime factors?
yeah, so, I see. So, so for this specific question, I remember when I was working through this, I had so many diagrams that looked something like this. So I would draw my axes of primes just sort of haphazardly. So these would be maybe my starting grid. So we have x1 up through, as you're saying, x log h. So just a bunch of things varying. And then when you want to prove something about higher Selmer groups, what you do is you choose some subset of these indices 1 through k that work really well for doing those higher Selmer calculations. Like, so for example, in these calculations, I had that one of my elements was ramified at P1 and nowhere else, and the other one was ramified at P2 and nowhere else. You sort of need to organize for that. But yeah, you choose however many you need to form the hypercubes to go as far up the tower as you want. And maybe when you do that, you select, we only needed 3 to go up to the 8 Selmer group. So you select your three axes that you actually want the primes to change, and then everywhere else you restrict to a single prime.
And you kind of just bury that inside A, sort of thing?
What is it?
You can imagine that being buried inside A or something.
Inside, sorry, what's A?
Inside your product of bad primes, just treat it as like another.
Yeah, it's sort of,
A fixed prime.
in the higher calculations, the primes that you fix in this way and the primes in dividing A are, yeah, treated exactly the same. Yeah. And then as I sort of alluded to at the beginning, just because I have this picture up, for all but one of the remaining intervals, you choose actually not a huge subset, only one on the order of size, maybe log h, or maybe even smaller. And then one of the intervals you really want to be really large, because that's the one that you're going to be applying Shadowtar to. Yeah. So there is this step where you start with one grid and you get a much smaller grid.
And then there's an analysis thing to say, okay, let's still cover this again.
You know there is.
Like
That analysis is in the section regridding, because you start with one grid and you end up with a different grid that's totally different. And this is section 6 of paper 1. So yeah.
Is what you just described being ready for higher work, this choosing the 3 things?
Yeah, that's in the context. So ready for higher work is a term that comes up in section 4 of paper 1. And it's exactly, you assume something relatively nice about the 2 Selmer groups so that you can play this game for higher Selmer groups. And this game for higher Selmer groups, I'll mention, is very, very delicate. Here's a question, which if you answer it, I will do everything I can to make your career really awesome. And the question is, how does CLK to infinity behave in the set, or the family of quadratic extensions of QI? So very similar to the sort of questions I can answer, but the point is that when you start with this base field, the actual minutia of how you do this higher work just breaks down. There is a certain part of the castle state pairings you get in this case that this method just looks like it can't control at all. Basically, whenever you try to do something like this, either this left sum ends up being something crazy mysterious, or it ends up being 0, and nothing in between.
Is the problem units, or like why?
Units is ostensibly the problem. The problem is something that people are aware of, which is that there's a symmetry in this case between the four-torsion of the class group and the dual four-torsion viewed. So, in other words, how I think of this, so in this case, you're looking at 2 infinity Selmer groups in sort of the case that Alex was talking about, in quadratic twists of Q2 over Z2. And the point is that the 2 Selmer groups of Q2 over Z2's twists and the 2 Selmer groups in the dual case, they overlap, and then you can't handle that overlap.